So once again, for those who came in late, the repo for the lectures is at CS109 2015. You've probably been to this one before. The full contents of everything is in the lec04 folder. If you just want to see the slides, it's 04-pandas-sql.pdf down here. And if you want to run the IPython notebook, then it's this first one, pandas and SQL.ipynb. So I'll start off, but I guess the big announcement to make just before we start is that the class location shifts, and it's in Science Center B, right? It's in Science Center B. That's down Oxford, go towards the big church-like building, and the Science Center's on the right. It's a much bigger class. We have better audiovisual stuff for the extension students, so I think it should be overall a much nicer place to do this. So my name is Rahul. I'm your head TF for this semester. So if you have any complaints about the course, you can contact me at any one of those three ways to contact me. Preferably email on the staff@cs109.org list, because if I can't get to it immediately, somebody else will. That way you won't be waiting. Okay, so how many people have heard of SQL? All right, so almost everybody's heard of SQL. How many people know how to program SQL? Oh, great, that's also quite a few. And for those who don't, it's really simple, and you'll be able to figure it out really fast, especially now that you have a working knowledge of Pandas, because Pandas is entirely built on the SQL relational model. So SQL's been around for a fairly long time, maybe about 25 years now. The first database is coming out, I think, in the late 70s, early 80s. It's a very, very well-established technology. The databases that go along with it, like Postgres, Oracle, MySQL, they've been around for lots of years too. And this is the one big reason to use them. They've been around for a very long time. People know how to optimize this. People have invested lots and lots of cycles into optimization of these pieces of software. And if you are ever caught with a problem where you have a huge amount of data and you throw it into one of these databases and things are not performing, you'll probably be able to find help. Much like Pandas, I think you probably realized by now that you can pretty much ask any question about Pandas into Google and something on Stack Overflow pops up, which is helping you out. If you haven't realized that, it'll be really helpful for the homework. Okay, so in this course, we're going to be teaching you a lot of data science, right? A lot of data analysis, some statistics, some machine learning, a lot of these nice, buzzwords, writing recommender systems, all these kind of things. But one thing you've always got to keep in mind at the back of your head is all of this nice research, all of this nice work you put in is useless if you can't actually make a product out of it. It doesn't matter what that product might be. You might be working at a company and you're trying to make a product. You might be trying to make a little website. You might be trying to write an article. So you want to have the ability to write to make this product out of it. And this is one of the problems, for example. I think this was one of the slides which was there on the first day. It took 3 years before the Belcore Pragmatic Chaos team managed to win the Netflix prize, but then nobody could use their solution. Because it was a great solution. It improved things by about, I think, 1% on the whole, which is a lot of improvement when you're talking about being at about 80%. But it was so complex, and it could not be implemented fast, so it was never implemented by Netflix. So in other words, we have all these sort of phrases. This is another one of the slides from the first lecture. We have all these phrases that we've put up over here, but a lot of the rest of the stuff, like business intelligence or decision making or storytelling, cannot actually happen if you don't have a certain amount of data management or data mining, if you don't have the setup to do that kind of stuff. So in other words, you might think that the analysis, the science, and all of this is kind of the most important stuff. But in many ways, the most important aspect, and one that you might end up spending a lot of time on in your careers, is actually the data engineering part. How do you get the data engineering to work? And this happens at two different places, right? So imagine you're Google, right? And you've written this whole big, nice algorithm based on PageRank, and you've made it, you've even figured out how to make it scale on millions and millions of machines, and you've created this index. But now you are still left with the problem of actually figuring out what happens when I go into Google and type. Those results should come back really fast. It's not enough to have made an index, right? So not only do you have to make an index, you also have to make the sort of user-facing product. And the user-facing product needs to be fast as well. So the engineering part actually comes in both those places, and both those places are equally important. So it's not only a question of an algorithm to make a prediction, but it's a question of also being able to search for the results of that algorithm. That is important. And going back to that Venn diagram, which was also on the first lecture, you can sort of take the three parts of the Venn diagram and sort of label them in a slightly different fashion. The substantive expertise, which you might be bringing in because you're a biologist or because you're a marketing expert, is sort of your quote-unquote your business intelligence. The stats knowledge, the computer science knowledge, the machine learning stuff you kind of you bring in as part of your data analysis skills. But there's a whole other part of these kind of hacking skills which you need to know, which is the data engineering part of it. And in this course, what we'd like to sort of do is sort of like, move you along in parallel directions in all three of these. Well, the third one, we can't really do that much because that depends upon the domain you're in. But in homework 3, you'll see that you'll actually have to solve a problem in which you'll have to figure out how much money a company must invest so that they can make a larger profit. And that's one of the things that you're going to have to tell the manager of that company. So along with the data analysis part, which I suppose is what the preponderance of this course is made up of, there's this data engineering part which you have to figure out. And that starts all the way from hacking, basically, and goes onwards to actually being able to set up these massive databases, to then being able to program on these massive databases, and all of these various kinds of things. So here's a somewhat longish, I suppose, quote from the US Chief Data Scientist, DJ Patil, from his book, Building Data Science Teams. And he says it's kind of important that his data team wasn't comprised solely of mathematicians and other data people. And that it was a fully integrated group. It had people who were engineers, who were marketers, who were all kinds of people. And they all worked with data. They all were able to take insights from it. They were all able to contribute, basically, as to how a product's design should work. The designer should have insights that help the engineer. The marketer has insights that help the machine learning part of it, and so on and so forth. Now, if you're a big, big company, I think at that point he was part of LinkedIn, you have the money to be able to hire a different person to do the data engineering, a different person to do the machine learning, and a different person to do the design, and a different person to do the marketing. But now imagine, as I hope, that some fraction of the students in this class are going to create startups, right? And you're like 3 people. And your startup involves machine learning in some fashion. It involves having a big database and stuff coming out of it. It involves having a web interface. It perhaps involves having a iOS or Android interface. And you're 3 people. So you need to sort of be a kind of jack of all these skills, or at the very least, you need to be dangerous enough to be able to do something with these things and know when your skill set ends, and to and sort of like consult somebody who's a better pro than you. So you need to know, A, you need to know the language, B, you need to know the minimum. So you need to have these minimum data engineering skills. Okay, so what do I mean by this? I mean actually quite a few things. Well, the obvious one is that you need to be able to code. You can probably be a business analyst if you take a point-and-click application or Tableau or one of these things and make a dashboard or something of that sort. You'll be fine. But if you're in the startup and you're one of like 3 or 4 people doing this startup, that won't cut muster. So you need to know, obviously, to be able to code whatever your language for coding is, and then you need to know certain ecosystems in which to code. So for example, if you're working in R, you probably need to know about data frames, and if you're doing machine learning in R, you probably need to know about Caret. If you are in Python, you probably need to know about scikit-learn, or and APIs. And if you're doing the web part of it, you probably need to know about Flask. If you're doing the database part of it, you probably need to know about SQL Alchemy and different such pieces of software. So that's the first part. Then, I mean, if you're doing something on a big cluster with big data, you might need to know something about Hadoop. You might need to know something about Spark. So that's the first part. That's the compute part. So that's just the actually doing the compute, right? That's not setting up any of this stuff. The second thing is, well, your data needs to be stored somewhere. If your data is small enough, like most of the data we'll see in this class, but not all of the data we'll see in this class, you can put it in a CSV file. And you can load that CSV file into memory on Pandas, and you're done, and you can go home, basically. Or maybe you're actually writing an application where somebody's clicking a button on your iOS app and is actually putting data into the database while you're doing stuff. So you actually need a real database. But even so, it fits into one machine. You're OK. You say, OK, I know how to deal with the database with one machine. And you go home. You're done with that. But maybe that doesn't happen. And you need a much bigger setup and so on and so on. So there are various ways you could do this thing, right? So there's like SQL. There's SQL databases like Postgres, like SQLite you might use. There's this quote-unquote big thing these days called NoSQL, which is like document databases like MongoDB, where you might be putting JSON files in there. You might be using Memcached, which actually caches the results of your web applications before it goes out to the browser or to the phone. So there are these various databases, various ways of storing things that you need to know. So that's the storage aspect of it. So we talked about the compute aspect of it, and we talked about the storage aspect of it. There's a third part, and this is what these days is called Devops, which is, OK, I'm setting up all of this stuff on Amazon, and 5 of my 100 machines went down, or 1 out of my 5 machines went down, depending on what your scale is. How do I immediately bring up this machine without having to worry about logging onto a machine, going to Amazon's website, clicking 152 different buttons, bringing your machine up, installing Ubuntu or something on it, and then installing your software stack, editing configuration files. You're not going to succeed as a business if you do that. You're not going to succeed as a startup. You need to automate all of that. So that part comes into DevOps. And we won't be talking about DevOps at all in this course, but it's something to keep in mind that you need to figure out if you're going to do any data engineering. And then the fourth thing, of course, is the most important, which is the product that you're producing out of this whole thing. It might be a website. It might be an API consumed by another website. It might be an iOS application, whatever, right? An iOS application also probably consumes a web API. It might be a visualization. Some of you may have seen these nice visualizations in the Boston Globe about what happens if the global temperature goes up by X degrees Celsius, how much of Boston will be covered. Have people seen this? If you haven't, go do a Google search for it. It's a pretty cool whiz. But the point is that all this whiz needs data at the back end. So you got to figure out how you're going to store that. So even if it's a story in the New York Times or in the Boston Globe, there is probably a data story at the back end which you need to understand how to do. So whether you're a journalist and you're writing a story, or whether you're a web application developer or an iOS application developer, or whether you're a data scientist in a big company or a startup, the product's always kind of important, and you need to be able to figure out what data engineering is needed to create this product. So obviously, this is different at different scales, right? If you're a 3-person company starting really small, you really don't care about a lot of the big stuff and so on and so forth. You don't have much data. You do the smallest possible thing that works, the so-called minimum viable product. And and then you figure out how to scale from that point onward. So you don't have to learn all of this at one go. But you need to learn the minimum stuff. And then once you get to a big scale, you need to be able to automate a lot of stuff and do a lot of the stuff in a very kind of simple fashion. If a machine goes down, bring another machine up, have multiple web servers, right, in case your traffic went up because you got Reddited or Slashdotted or whatever it is, whatever the cool stuff is these days. It used to be a Slashdot when I was a grad student, but I think now it's Reddit. Am I right, or am I? No. The place which brings a lot of traffic and brings down sites. Okay, so this then brings you to the question: what kind of data storage do you need, right? If you can just store everything in memory, you might as well use Pandas and be done, because you have it in memory, you have a CSV file from which it came. That, of course, also depends on whether this is a read-only situation or whether this is a read-write situation, whether whatever application you're doing is actually writing back into the database or not. And then you can play this game where you ask yourself these questions. So what happens if things do not fit into memory, right? I have like this machine with 16 gigabytes of memory, but my data set is too big to fit into 16 gigabytes of memory. So maybe I can only get a part of it at a time, right? So I get this part of it, but that part of it needs to remain on disk. So then I might have some technique by which I can store a good amount of this data set on a disk. And typically that technique is called a database, where some part of it gets loaded into memory and some part of it remains on disk. Okay, so you got this machine and you've got a huge amount of disk in it and still everything doesn't fit on this machine. So now you say, okay, I'm going to partition my database on this big cluster, and then you come up with stuff like HBase, or Google Bigtable or one of these kind of things where the data is actually stored at multiple places, not just because it didn't fit on a particular machine, but because you might want the access patterns of it might be also somewhat different. The original reason that Google actually came up with Bigtable way back was because when they first started with Google Maps, they wanted to come up with a really quick way of loading maps, which was if this is like the Science Center and this building out here, all these stuff around it. So that was the original reason they came up with Bigtable as a mechanism to do that. So if it doesn't fit, you might want to put these things on a cluster. You might also need to use different parts of the database, like Google needed in this particular case. Then you might actually do this on a cluster. It may get even worse. So if you're in one of these newfangled astronomy experiments like the LSST, which is going to produce like multi-terabytes of data per night, you're not going to be able to do the computation at any place except the telescope itself, because you're not going to be able to transfer all that data over. The thing that goes slowest of all things is network speed. It's like disk keeps burgeoning up very fast. Memory a bit slower than that. And making huge bandwidth connections between places is even slower. So at some point, you may actually have to think about this from the perspective of, okay, I have this humongous data set, and I actually need to do all my computations right at where the data is. And so I need to have some story as to how that data is actually stored there. So these are sort of the things that you think about, as you're scaling up from being a small sort of like company to a large sort of place where multiple things are done. But then there's a completely, if you like, orthogonal set of things. So that was based upon size. But size is not the only thing. It's the access pattern your data has. So typically, you might have a relational access pattern where you have one or more tables, and there is some connection between these tables, right? So one of the example that I'll work with right now has it's a somewhat dirty database but dirty in the sense that it's not cleaned at all, from the Federal Election Commission of who contributed money to which candidate in the, I think this is in the 2012 elections. And so amongst the contributors, right, you probably want some kind of column which tells you who they were contributing to. But you don't want to necessarily store all the information about who they were contributing to on every line. Because suppose there were 1 million people contributing to Barack Obama, then you're storing Barack Obama's name 1 million times, which is a manifestly huge waste of space. So what you typically do is you assign Barack Obama a number. Say, let's call Barack Obama 12, and you store the 12, which is still a manifestly huge amount of space, but it's less than Barack Obama, right? And then in another table, you have a table which looks it up. It says 12. Oh, 12 is Barack Obama. And 13 maybe John McCain or something of that sort. So that's the sort of notion in a relational database where you basically have a key which points from one place to the other. The ones you are most likely to use in the near future are probably Postgres. I'd highly recommend Postgres as a database to use. It's open source. It's very fast. It has support for JSON. It has all kinds of things. SQLite is the other one, which we'll use today, and actually basically creates a file on your disk and supports most but not all the things that relational databases typically tend to support. But because it's so blindingly fast, you can actually use it to do a lot of analysis on data which does not fit into the memory of your computer. So that's a really good use case for SQLite. It's also used just about everywhere on your computers. If you're using any one of Safari, Chrome, or Firefox, they use it to actually store data. If you're on a Mac, the Mac operating system uses it to store preferences everywhere. I'm sure Windows uses it at multiple places too, and Linux uses it to store a whole bunch of system data as well. So relational databases, so this Postgres, the SQLite, HBase itself is, HBase and VoltDB are somewhat newer. HBase is the open source version of Google's Bigtable, but it is a relational database. And along with VoltDB, it's actually a relational database which stores data in a slightly different fashion. And I'll come to that in a second, but I just wanted to point that out. Then there are document-oriented databases like MongoDB, which basically stores file after file of JSON, which Postgres also does particularly well these days. So the need for MongoDB, I think, is a bit less these days, but it's still a good alternative. And again, it's one of these things where so many people have used it. If you have a problem, Stack Overflow will basically help you out. Then there are key-value databases, which are like Riak, Redis, and Memcached. And these are sort of more specific, but they're like super fast. And the only one thing they do is you give them a key and they give you a value. So for example, if many websites will do this. Like you go to a website, you log in, and it gives you this nice kind of look of your page, and it takes a little bit of time to load. But the next time what it does is it caches the entire HTML of the page with a key, which is your session ID. So next time you go there, it says, okay, that's this person from so-and-so IP, blah, blah, blah. That's Rahul. Okay, let's just show them this HTML. Let's not regenerate the whole thing. So that's one example of where you'd use that. But you use it in multiple places. Every time you need to store a dictionary, that's basically a key value store. And then there are some more sort of like, special databases like Neo4j, which is a graph-oriented database, which people use to store, Twitter networks and Facebook networks and stuff like that. Because the query patterns of trying to find the nearest neighbors in a graph are actually much faster in those databases. So the takeaway message from the slide, if you like, is you use a database depending upon what kind of data access that you need. And if you don't have a overwhelming reason to use any other database, use a relational database. Because it's just been worked on for such a long time that people know the ins and outs of how to optimize it. OK. So today, the focus, so we'll be having this sort of like a data engineering subtrack, if you like, in this course as time goes on. And we'll start off with sort of SQL today and a kind of comparison to Pandas in many ways, because you'll see how close the models are. And we'll keep going on from that point. Later in the semester, we'll go on to doing stuff on Spark. And Spark itself will have to access data from a data store. So we'll access data from an HBase data store and see how you do that in sort of the large, in one of those larger sort of scenarios, basically. So we'll keep going, sort of like drumming this, if you like, data engineering drum as we go through the semester, showing you different kind of models in which you might want to do it. OK. So these are the questions we're going to sort of tackle today. The first question is, what is a relational database? What grammar of data does it follow? In a sense, this notion of a grammar of data is the idea that it's one of these ideas which I think would be kind of a foundational thing that you can take out of this course is, here's a new data system, here's a new data set. Now, what do I want to do with this data set? Can I split up what I want to do with this data set into a set of verbs? And if I can split out what I want to do with this data set in a set of verbs, then I can go to a new data system, a new database system. Tomorrow you go and play with Cassandra or Voldemort or any one of these systems, and you're like, how does it do these verbs? And besides these verbs, what else can it do? And so it's a way of kind of orienting yourself as to what a database system can do for you and whether it's an appropriate database system for the application that you're writing. And we'll talk about how this grammar is implemented in Pandas and how it's implemented on SQLite in SQL, basically. OK. So the relational database actually came with this kind of notion that people wanted to get out of this notion of doing very sort of low-level programming, which is that they were basically going on disk and saying, well, I know this data structure. It takes about 20 bytes. It starts at 20 bytes, and it's about 50 bytes long. And there's all kinds of stuff packed up in it. And I have the specification for how it's packed up in it in my C header file as a struct and so on and so forth. And I don't want to take it out like that, because then I have to go to the next one and go to the next one. And I have this whole sequential access paradigm, right? Because I have the first 50 bytes here, and then I have this 50 here, 50 here. And I want to go down there. I have to seek those many bytes down and go here. So people started asking the question, I don't want to know how to do this. I just want to know how to select data from a set based on some criteria. I don't care where it is. Just get those rows to me. Just get whatever matches that criteria back to me. And you've done this in Pandas when you say, df.query age greater than 52 or something of that sort. You're saying, I don't care how you get those rows with age greater than 52. Just get me those rows greater than 52. And so this sounds like something kind of obvious, but it wasn't about 25 years back. And people never thought that, that relational databases would actually work. But obviously they did. And we're better off for those. So the entire model is something you're actually familiar with from seeing Pandas so far. And the idea is that it's a bunch of tables. Actually, maybe not, because typically in Pandas you've seen one table. But the whole idea of relational database, it's a bunch of tables, and they're related to each other through some common data values. And we're going to call these data values keys. Each row, basically, represents the attributes of something. For example, if it's a table of tables, it might represent the attributes of the legs of the table or the thickness of the table or something of that sort. Everything in a column is one of these attributes. So your columns might be like your thickness or your, the number of legs, although we do have tables with 3 legs, so that's fine. The general expectation is that one of these cells, which is the intersection of the rows and the columns, is supposed to be atomic. This is not true in Pandas, by the way. In Pandas, you can store lists and that kind of stuff within a cell of your table. But it is true in SQL that you want these to be an atomic thing. Again, there are exceptions, but typically you want this to be one value of some type or the other. And then tables are related to each other if they have certain columns, which we call keys. Like, for example, the ID of the candidate, the thing that identified Barack Obama as 12, which connected one of these tables to the other. So here's that example I was talking about. You can see that actually Barack Obama is 20, not 12. And you can see that candidate with an ID 16 has been, who is Mike Huckabee, has got contributions from all these folks in the table in the background over there. So that's the basic model. It's a really simple model. It's 2 tables, and they're connected in some fashion, in this case by 1 column. Now, the things inside these columns have types. So there's a first name here. There's an ID, which you want to be an integer just because of storage. You want it to be something small. You don't want it to be big. And you want it to be unique, typically, because it's something you're going to look up things on. So that's the second thing to remember, that one of these keys, if you're going to look them up, you typically want them to be unique, because you're trying to say, oh, well, these were all the contributions to Barack Obama. And so the number 20 should uniquely identify Barack Obama. And typically in the table, that's called a primary key, because it's in the candidates table in this case. It's the one that's telling you that that's the primary lookup for who Barack Obama is. And I'm going to use that in every other place to try and figure out, as if you like a proxy for Barack Obama, I'm going to use the number 20. And so that number needs to be unique. And it's called a primary key. The primary key, perhaps you'd want it to be an integer, simply because that's a very quick way, that's a very quick and sort of like low space way to store something. I mean, imagine you could actually use a 128-bit unique ID or something of that sort, right? Or a private key or something of that sort, something really, really long. But that would kind of defeat the purpose of doing this in the first place. But that's also unique, but it's not small. So you want something unique and small. It doesn't have to be globally unique again. It needs to be unique within the context of that table. There shouldn't be 2 20s in the candidates table. So that's the scope in which this uniqueness is needed. And then you go back to the basic scales of measurement that I think Hans-Peter talked about in the first lecture, and which were come up with by Stevens in 1946, which you have this quantitative scale, you have this ordinal scale, and you have this nominal scale, and now you want to represent these, right? The quantitative scale is going to be represented either by integers or by floating point variables. The ordinal and nominal scales, well, the ordinal scale, you have a choice, right? It's a set of rankings. For example, if you're writing a recommender and you're looking for a 1-star, 2-star, 3-star, 4-star, 5-star, that's an ordinal scale. And you might but you might just represent that as a set of characters, 1, 2, 3, 4, 5. Or you might represent it as in databases which support enums, you can represent it as something which can have only 5 different values. Or you might just say, what the hell? I know it's not going to be anything less than 1 or greater than 5. I'm just going to make it an integer because that's a simple way of doing it. So that's kind of your choice. The nominal, you're typically going to use a text type or a character type or a varchar type or one of these types, these stringy types. And I'll come to that in a second when I show you how to set up one of these tables. Okay. So the idea of this grammar of data thingy I was telling you about was that it's been there for a while. SQL's had this kind of for a while, and Pandas has this. But Hadley Wickham formalized this when he came up with dplyr. And he said his basic notion was this, that so that we can recognize things amongst these various systems, we're just going to provide verbs for simple things. These are functions that correspond to simple tasks. So things like I want to select a column, I want to select a row, I want to add something, I want to take something away. These kind of simple notions. And the second big notion he had over there was that the backend does not matter. It doesn't matter whether you're using a data frame in R, or you're using a data table in R, or you're using a data frame in Julia, or you're using a Pandas data frame, or using a SQL database, or whether or any of these things. It doesn't matter. In our particular case, I'll show you in both Pandas and SQLite how these things correspond to each other. But one thing that's actually kind of good to know is that this kind of notion has been now implemented in many different backends. So you're familiar with Pandas. Spark also has data frames in which you can actually select things and so on and so forth. And it will actually do it over multiple machines for you, but with the same kind of syntax. Impala is a SQL clone for large clusters with HBase and Spark running on them. Pig or Pig Latin is a SQL-like language to query Hadoop clusters. dplyr is, of course, there in R. IBIS is a new creation from the author of Pandas. And Blaze is a similar library which tries to do the stuff for large amounts of data in Python, implemented by the folks who bring you Anaconda at Continuum. So there's lots of different efforts. But all of them basically have this model of this kind of, like, if you like, this data frame-ish kind of model, in which there is a key set of verbs that you're going to do. And once you know this key set of verbs, you're kind of set in using all these different kinds of systems. And if a system does not have this key set of verbs, you should try and pigeonhole its operations into this key set of verbs and figure out what the similarities and differences are. OK. So all of this is fine, but why bother with all the SQL stuff at all? Well, you want to be able to do these core data manipulations no matter what the system or this data frame stuff. If things don't fit into memory, you will have to use relational databases. If things need write access, you will have to use relational databases or something else, but let's just say relational databases for the time being. And once you have this kind of notion of this grammar, if you have any other one-off questions, for example, how do I cut stuff into bins in Pandas, which uses pandas.cut, for example, you'll actually find lots of good documentation on Google Stack Overflow. Oh, and there's one resource which I hadn't talked about earlier, which has lots of good snippets on how to do things. It's the URL there, chrisalban.com, and has tons of good little snippets for Pandas and so on and so forth, which might help you in your homework in these next 2 weeks. OK, so let's go to the notebook. And you guys should let me know when this is actually readable. Is that good? Or is it too big? Maybe a bit too big. Let's go with that and let's see. OK. So what we're going to do here is, as usual, we're going to have our usual incantation at the beginning. But we'll start with relational databases, and we'll go from there. So I'm going to run this first cell just to get things going. Actually, I should just restart this whole kernel. OK. So now let's talk about populating the database. This is a little bit outside this notion of this grammar I was telling you about, but it's kind of important that you know how to populate a database. The thing is that it could possibly be different from database to database. So some of the things I'll say here, and I'll tell you which one is which, will work for any database, and some of the things won't. So one of the key things about relational databases is that unlike Pandas, which tends to figure out what the data types are, and in fact the mistakes of its figuring out what the data types are actually a good way to clean the data, per se, as you might have discovered in the homework already. SQL and SQL databases need a specification. They need you to tell them what types things are. So it's a little bit more constrained from that perspective, but with constraints comes performance usually. So it's always, if you know your data, and if you know your data seems to be of some kind of regular type, you should embrace this. Particular constraint. So here, I'm going to try and get these two, sort of model these two tables. And I'm creating two tables. The first one's called candidates, and it has an ID, which is that, as you can see, it says integer, primary key, and it says not null over there. And these are kind of all important things. If you are going to have an identifier, that identifier better not change. So it should be unique. So that's the primary key part of it. It better not be null. So null is sort of the equivalent of Python's none. It's a quantity where I'm going to sort of, SQL has this notion that I'm going to not represent a piece of missing data as minus 99 or minus 9999, as you might have seen in CSV files at some point, or sometimes minus 9 if you go to like the census files. But they're going to say, oh, it's actually a null. I don't have data here. I'm just going to come out and tell you that I don't have data here. And it doesn't matter what type it is. I can call it a null. If it's a string, I can call it a null. If it's an int, I can call it a null. If it's anything, I can call it a null. So that's the not null part. You don't want that integer to be a null, because otherwise, what's the point? You're not looking anything up. And then the rest of them only has the party, which is not null, because I'm only considering Republicans and Democrats out here, and I want to know which one is which. And the first name, last name, and the middle name, all of them, if they're null, that's OK. You could probably have a candidate whose name was space, or something of that sort. It's perhaps not the best kind of data modeling, right? Because you would kind of expect that maybe you ought to have at least a name for the candidate. So you might want to make at least the first name or the last name not null over there. But it's a permissive kind of modeling. And that's how you always want to start. You always want to start with the modeling that's kind of permissive and then kind of tamp it down as time goes on and you understand your data set a little bit better. And then I have a similar sort of thing for contributors. Obviously, I want that ID to be not null either. And notice that I want the contributors to be kind of auto-incremented over there. There's this little thing which says auto-increment. And most databases will support this. And what they do is the next time you add a new contributor into the database in some fashion or the other, it'll just automatically give you an ID. So it'll start with 1, and then the next one will call it 2, and the next one will call them 3, and so on and so forth. And again, here is the last name, first name, last name, middle, street, city, all kinds of data about this person. The date that's put in out there. And notice that the date is a different type. It's a date time type. And then you have a candidate ID, which is an integer not null. And here's sort of like somewhat strange incantation. And this is the incantation which actually connects the two tables. It's basically saying that there is this particular attribute, this particular column in this table called candidate ID. It's an integer. It cannot be a null. And I don't want it to be a null because I'm referring to a candidate. And I haven't allowed the candidates to be null, so that one better not be a null. And it's a foreign key, basically. So candidate ID is a foreign key, which references the table candidates and the column ID. So that's just a little piece of, it's not part of this text over here. It's just this additional thing which says it's a foreign key. Candidate ID is a foreign key, and I can have multiple such incantations if I had multiple foreign keys to different tables. Foreign key, candidate ID references candidates of ID. So that's the table, and that's the column in that table up there. So that's the setup. So if you're new to Python, there's this 3 quotes thing, which lets you put things on separate lines. That's all that's happening in that particular cell. Right now, I'm just making a string with the schema in it. All right, so let me run that. And I'll set up some code here, which actually allows us to connect. So in Python, has this very nice API. It's called the Database2 API, the DB2 API. And that allows you to connect with any SQL database and use the same syntax to work with it. So that's one layer of it. And that's what's happening over here. Basically, the spot start is just the current folder. And in this current folder, I have a database file. And I am basically going to connect. And I'm going to return the connection. That SQLite-DB is just the connection to the database. That's what getDB does. And then in initDB, which is where I want to create this database up, and I want to create it and populate it with these tables, what I'm saying is, well, let me just get the connection to the database here. Once I get the connection to the database, I'm going to get what's called a cursor on the database. And then I'm going to execute a script, which I'm giving to it from that schema, that big thing up there, the create table and so on and so forth and all of that stuff. So that's going to actually create the tables for me. One thing which is kind of critical to remember about databases is that you need to explicitly commit in databases. So relational databases have this notion of transactions. That's the other reason why relational databases are really important. Imagine that the following thing happened. Suppose you had multiple tables that you needed to update, right? You're selling a product. And while selling the product, there are two tables you need to update at the very least. Let's make a very simplified product selling situation. You need to decrement the number of products in your inventory, and you want to charge the person's credit card. So you want to make that you want to make that node in your database. Now, if something happened to your system in between those two, right? Like a squirrel came off and chewed off the wire in between your two machines where you were storing this stuff, then either you charge the customer's credit card and have not incremented your inventory, or you have incremented inventory but not charged your customer's credit card and ship the whole thing out for free for them. So you don't want to have that kind of thing happen. It's kind of worse for a bank transaction as well, right? I mean, something went out of an account but didn't go back in or something of that sort. So that's why you have transactions. What you would do is you would only commit after these two things happened, after you decremented the inventory and you incremented the credit card table. And then you would commit. And so either those two things would happen together or not at all, basically. So, and that's a good thing. You want either the whole thing to have gone completely kaput or not kaput at all. You don't want it to go half kaput, because then you have some very sad customers or very sad companies. So then at this point you commit, and then you return the same connection you got over here. Okay. So just going to run those two. Oh, I think I already did. So that's the database creation part. I have these two files. Did I actually? I may not have put these files in. I may have forgotten to put these files in that. Pardon me? The TXT files are not there, right? So actually what I'm going to do is I'm going to replace this on the fly by a URL. So we can actually do this here. Let me just do that fast. So I think I forgot to do that. Bear with me for a second. Okay. So I'm just going to actually paste the URL right in here. Okay, so this one is here. Okay, I'm just going to make this a bit bigger so it's easier to read. So you can get the data. I'll make it smaller again. This is for those following along. If you're not following, if you're not trying to do this as we go on, then you can just watch what I'm doing, and you'll be fine. So you can either just store it on your local machine, or you can just put this directly into the read CSV, because Pandas will pick it up from the read CSV part. And I'll give you a minute or so to do that. So the first one is the candidates.txt. You can just paste that second URL over there. And then the second one is contributors with candidate ID.txt. Shall I go ahead, or? Yeah? Okay. So I'm just going to read the candidates file in here. The separator is a pipe symbol over here. Yeah, I'll make this a bit smaller now so we can actually see what's going on. And then the next thing I just basically, and I'm storing this in a data frame called dfcanned. And then in the next one, I'm basically reading the contributors with candidate ID.txt, and I'm storing it in a rather, I suppose, poorly named data frame called dfcwci, which really stands for data frame candidate with candidate ID. But it's a mouthful. Okay. So it has some user IDs over there. But if you remember, if you go back to the table, back a little bit further up, if we go back to our definition of the table, over here, we wanted this ID to be auto-incremented and set by itself. And the ID was not, when I actually looked at this data, the ID was only there for some of them. So I'm just going to delete that particular column over here. So that's the next thing I do here. I just delete that column. Okay. So we're just loading all the data into Pandas, and the reason we're loading the data into Pandas right now is because I'm going to show you different ways in which you can insert the data into a database. And one of the ways is to use Pandas. So let's start up our database. We're just going to init the DB. Oh, I have not run those, I think. So let's make sure I've got those going. Okay. And I'm going to use a particular piece of a particular function that's there in Pandas called toSQL, which will basically take the argument of the table, candidates and contributors, and put those appropriate data frames. So in the candidates table, I want the dfcann data frame. The contributors table, I want the dfcwci data frame. And it'll use this connection that we got, DB. If the table exists, and it should, because I just ran init DB, it's just going to append it. It's going to insert all these things inside the table. And it's not going to take the index. Remember, in Pandas, the index is this little thing on the left over here. And that means nothing for the database, so it's not going to put that in. OK. So now we can start off on trying to do our various things. So we're going to use, so rather than do SQL right on the command line, we're going to be actually using the Python DB2 API. And then we're going to cheat a little bit and actually wrap it with a Pandas data frame so that it kind of looks nice. So, and I'm only doing that for beauty and not for what comes out. You'll see what's going on over here. So over here, I'm just going to do a select star from candidates. That's the first thing you'll see. And what select star does is that it basically is just going to give you all the rows. And what the star part tells you is that it's actually going to give you all the columns in all those rows. So it's going to give you the entire table if you do a select star from candidates. So that's the first little piece of SQL. That's equivalent to just saying df on the on the Python line and getting the entire Pandas data frame out. So let's run that. And it runs it. It executes it. You can see I've put it into this little variable which is SEL for my select. And I'm going to have this cursor, and I'm going to execute the cursor, and I'm going to get back a result from it. And once I get back a result, I can use fetch all to get all the results I got, or I can do fetch one if I wanted one. But fetch all is what the DB2 API gives me as one way to get everybody. And here you can see that it's actually put it into this set of like list of tuples, if you like, of all the results. With the ID, the first name, the second name, I forget what the none is for. I think it's for the middle name. And we only have it for Christopher Dodd and Fred Thompson. And whether it's a Republican or a Democrat. So that's the output that the select statement gives us. OK, all very nice. Let's delete it. Let's delete our table. Notice that after I delete the table, I put in a db.commit. And that's because it's not actually going to do anything at like commit. So at that point, you might ask me, why didn't you do it at the previous step when you were doing the select? The select is a non-destructive thing. It just gives me something from the table, so I don't need a transaction for it. I'm just trying to get output from the table. The delete, on the other hand, is destructive, and it goes with the same kind of thing that you have with your credit card, that you actually don't want half of the stuff to be deleted and half of it not. So you make sure that you commit the transaction right at the end of what you do. OK, so let's delete from candidates. And then let's try and fetch all, and you'll see that there's nothing. So this is not the only way you can populate a database from Pandas. It's a really nice and fast way. I find it like a nice little trick. But if your thing was bigger than memory in the first place, you're not going to be able to do that. So now here is where things, whenever you're inserting, especially if you're doing it in a website, you need to be extremely careful. You shouldn't use Python's, Python's percentage format syntax. And the reason you shouldn't use Python's percentage format syntax here, it doesn't make any difference. You're putting it in a script. It doesn't make a huge difference. You could. But if you do this on a website and somebody starts putting actual SQL syntax in your command, in one of your text fields, you might basically end up wiping out all your student records. So this is a fun XKCD cartoon. Did you really name your son Robert, bracket, semicolon, drop table students? And so these are the SQL injection attacks. I believe, actually, I may be wrong, but I believe the Ashley Madison attack was one of these kind of drop, did you name your son Robert drop table students? Well, it wasn't exactly drop table, but I could be wrong. OK, so the way you're going to do this is basically you want to insert all this information that you have into this candidates table. So you want to insert the ID, the first name, the last name, the middle name, and the party. So you're just going to open candidates.txt. In this case, you should download the file from that URL and do it if you're going to follow along on this particular one. Or you can just run the previous steps and keep with what you got over there. So what I'm doing out here is basically I'm just going to read the file. I'm splitting on the pipe symbol. And after I do that, I'm going to get all the stuff from the line. And then I'm just going to create a tuple of the things I want to insert. And when I insert, I'm going to take this insertion code up there with the question marks. And this is because I could have actually done percentage %s, percentage %s, percentage %i, percentage %s, percentage %s over there and done a Python format string. But you don't want to do that. Never do that. Just make it a good habit. Never do that even here, even though you could get away with it here because it's just an insertion that we're doing on the command line over here. Don't get into those problems. So here you're going to do this insertion. And what I'm doing is, this is going to be somewhat slower than what Pandas did because I'm going to actually insert it row by row by row by row. But I may not have a choice if I have millions and millions and millions of rows of data and I don't have that much memory. This may be the way I have to do it. So I hit this, and you can see what it's doing. And for each one of these, it's going to send the database this stuff, and then it's going to actually send them this tuple of information. So it goes and does that. And now, because I don't want to write the selector, this query each time, I'm just going to wrap it in a little function, which I've called makeQuery out here. I have some kind of select statement in there, and I do a db.cursor.execute, and I fetch everything. So this way, it's just a little bit simple. It's just a little bit of less typing. And I'm going to do a select star from candidates, which is going to give me the same result that I had before. And at which point, I'm going to go in and delete the whole thing. And you should, if you've been following along, and if you want to use the SQL, the SQLite command line, only then should you use the next part. If you don't want to use the SQLite command line, don't do this next part. Don't do this deletion. Okay? Because then the other stuff won't work. Okay, so I've deleted this again. So this particular thing is not very useful to show, actually, in many ways, because it changes from database to database. But because SQLite's so easy to use, I'm just going to show it to you anyway. You just have to take out the header, the header from the thing. So I'm just using this little tail command in bash to do that. And then I'm going to use this import command, which is very special to SQLite. This is all SQLite syntax over here. And I'm putting it into this file, can.const.db. So if you don't have the SQLite command line interface, do not follow along here. Just go back and populate the databases using Pandas. But for those who have this, you can see that this works as well. OK. So at this point, I can finally, with the setup, I can talk about these single table verbs. So here's the deal. Here's the kind of commands, which this is actually kind of blindingly obvious, probably. But these are the commands which you think that you might want to do with a table of data. And that's what it is. The first thing is query or selection. You're basically trying to pick out rows of this, which match some criterion. That's your select, basically. The second thing you might want to do is you might want to sort it by some attribute. Give me the candidates who got the most money, or well, that's actually more of a group by. So let's go back, and it might be something actually simpler to sort by. You might want to sort by the contributor who paid the most money, or something of that sort. So that's a sort. Then you might want to select columns, and that's in database language. The first thing is called a selection. The second thing is called a projection. What you're doing is you're basically taking this table and you're projecting and trying to get a column or a few columns out of it. You've seen this in Pandas with the df with the double bracket syntax, as to get stuff out of there. Okay. The next thing is to select distinct stuff. You want to find unique stuff. That's typically another use case that you want to know all the rows for which there were, what are the unique values of a column for all the rows. So what are all the unique people that were contributed to, and things like that. Then you may want to assign, basically. So you may want to create a completely new column, which is somewhat more complex to do in SQL, because remember you did that entire incantation which said create table blah with all of these columns. So now you got to change it and add a column. Much simpler to conceptualize even in Python, in Pandas per se. So but that's basically adding a new column, or for that matter, just taking an existing column and rewriting some parts of it. Okay. After that, we have we might want to calculate some aggregates, like averages, maximums, and so on and so forth. We might want to do a sample. We might want to do a group aggregate, which is the thing that comes from doing Pandas group by, which is I might want to group all the contributions by the candidate and calculate the mean contribution to this candidate, or calculate the sum of all the contributions to this candidate to see which candidate got the most money. So that's that kind of question, how you do this group by stuff. Okay, and then finally, you might want to delete, basically. And I don't happen to know how you do this in dplyr, so I'm going to ask one of the R experts in this room to file a pull request against this and tell me what goes in R to do this. I thought I'd put the dplyr and stuff here as well because I know there are lots of R aficionados here, and so if this helps you map to something you've done before in R, all the better. And for deletion, the way we do deletion is we either use drop in pandas or masking, or we use delete where in SQL. So let's run some of these examples. I'm just over here, just kind of looking at this file of this table of contributors over here, just to see its structure, so that I can figure out how I'd like to do some queries. So here's one of them. This is in Pandas. This is saying I want the state of Virginia and the amount of the contribution less than 400. Okay, so we run this. And notice the syntax with query. You don't have to actually inside it put that df inside again. So the syntax is actually quite simple. So there you go. It's going to give you everybody from Virginia who contributed. Note that there are amounts of like -100 and -34. I have no clue why this data set has that, except that I haven't cleaned it. So that's, it was kind of weird when I saw it. OK. We can do the same thing by being very explicit and having these brackets in Pandas, where you have sort of like the square syntax. It's not a function. And basically, you're creating a Boolean mask inside. This is Pandas masking. Basically, you're creating a Boolean mask inside, and it's going to be places where the state is Virginia. They're going to be trues, 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 trues there, and falses everywhere else. And then when the amount is less than 400, there's going to be trues, 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 trues there, and falses everywhere else. And then you're going to do a bit, sort of quote-unquote bitwise and between the two. So you're going to get wherever it's true and true, it's going to be true, and everywhere else it's going to be false. And that's what gives you this result here. And it's going to be the same. OK. So how do you do this in SQL? Let's see how we do this in SQL. Again, meanwhile, I have two little pieces of code which I'm doing as support code for showing things nicely. All that this is doing is it's finding the columns of the contributors table. And this one is going to make a nice little data frame from the results. Remember, we had that list of tuples coming out, and you can see one of those over here. It's going to take those list of tuples, and it's going to put them into a data frame for us to see what the output is. I won't go into this right now because it'll take too much time. But you should look at this code and convince yourself that it's actually doing the right thing. OK, so here's the query I'm going to make. I'm going to do select star from contributors where, it's actually kind of really nice syntax, state is equal to Virginia and amount is less than 400. It's exactly the same query, but I'm doing it in SQL. And the output, of course, is this set of tuples you get, which I have sort of like nicely sort of done this make frame out of it, which gives you this nice kind of output. And you can see it's identical. There are other ways you could do this. You could, for example, do a select star from contributors where state is null. This is probably something you want to throw out of your rows in this particular database because presumably the contributor lived in a particular state, or maybe this was a Washington, D.C. thing. But the city is Braschat, which I have no clue where it is. With a 4-digit zip. There are 4-digit zips? I don't think so. So I think this was just bad data. Large cart 77 at Braschat. OK. Travisborn. OK, that's a bit of a reasonable name. I thought there might be something funnier. In Pandas, of course, you can do the same thing by doing an is null, as you might be familiar with from our labs. And you can also do select star from contributors where state is not null, which is going to give you a whole bunch of states. So instead of actually doing it, I'm just going to look at the size. And you can see you'll get the same size if you do the not null in Pandas. So these are all examples of like select wheres, which are this basic thing to do with the select verb. There are other forms of it. You can do select. You can basically do select star from contributors, where the states in Virginia and Washington, for example. So that's an in, and you're generally going to use this if you have 3 or 4 things that you want to do it with. And that's going to give you Virginia and Washington there. Again, Pandas follows exactly the same way and looks for an is in. And so you can do that as well over here. Then if it's a floating point variable on integer, you can do between 10 and 50. A critical thing to remember in SQL is that if you do 10 and 50, it's inclusive of 10 and 50. So that's where the amount is between 10 and 50. And that's the same thing in query. If you were doing this, by the way, in the sort of like long form with a Boolean mask, you'd have to have two separate clauses to do this. In Pandas, if you want to sort, so this was select. So this is select where. Or in Pandas, just query. Or just the box kind of operator in Pandas. And in SQL, it's just select where. It's really simple. It's one of the, it's probably the thing that you'll use about 70% of the time when you work with SQL. So, you know, that by itself is just almost like I would say enough to know. But some of these other things are kind of useful, like sorting is useful. In Pandas, sort by amount. If you want to sort and you want to sort descending, you do ascending equal to false and sort. By the way, I'm just doing a head 10 at the end of all of these just to show the top 10. And the reason it works is, of course, remember that this is something you've got to remember very carefully when you use Pandas, that when you do a Pandas thing, like a sort or something, the sorted result is in the output. It does not happen in place. This is fairly critical to remember. You might be a gotcha in your homeworks as well. When you do something.sort, like df.sort, you must make a new data frame equal to that old data frame. So you could call it like df sorted is equal to df.sort on some column, basically, because otherwise, you're doing a df.sort, it's going to give you an output very nicely out here, which is sorted. And then the next line is going to be back to the old df, because you didn't do anything with the output of df.sort. If you don't want to do it that way, and I would suggest that you don't do what I'm saying right now, you would put an in place equal to true. And that would do the sorting in place, or do any of these commands in place. But don't do that, because that will lead to sort of like errors. Just remember that you have to assign the result of any Pandas function to a variable. The only reason you would actually want to do this in place is equal to true if the Pandas thing was really, really huge. And one of those places where it's really, really huge, and I actually kind of lied about this to you, but I'll come clean, is that Pandas can actually read an entire database table which is larger than memory. What it just does is it doesn't actually put it into memory. It says, oh, I've got this database table in SQLite at the back. I'm not going to do anything. Now when you do a pandas.query, give me everybody who has an amount less than 400, then I'm going to go and fetch the results from the database. So it does this lazy fetching business. So you can actually use Pandas to talk to a database entirely and not learn any SQL if you like, but that would probably be a bad idea, because then you won't understand the model as well. Okay, so here's a sort. In SQL, when you do this, instead of saying sort, you say order by. So I'm again ordering by amount, and if I order by amount, it's going to go low amounts to high amounts. So apparently the lowest contribution here was minus 2592, which I have no clue. And then if you want it to be descending, you put the ESC. And one of the things I'm doing in this notebook is and you should do this too, and it's a very conventional thing to do, is that all the SQL commands are usually in caps, not in small letters. So there's a order by over there. If I want to get columns, I just pass it a list of columns in Pandas. If I want to get columns in SQL, I just pass it a list of columns in SQL. It's exactly the same thing. Select first name, comma amount from contributors. I can combine that with var, by the way, if I wanted. Select first name, comma amount from contributors where amount is less than 400. That's perfectly fine as well. And I can see that, and I'll get the same result. To get distinct stuff in Pandas, well, here I just do a count to see that there are 175 of those. What I can do is I can do the function drop duplicates. And drop duplicates will drop duplicates. You might have heard of also the command unique, but unique actually ends up giving you a list of unique things, not a Pandas data frame, which removes those duplicates. So here you can see when I drop the duplicates, I go down to 126, and I can look at what it looks like. And you can see there's Ajay, Stephen, and Aaron's Don. And if you actually go back and you look at some of these, you'll see that Don shows up 3 times, and now Don only shows up once. So this has kind of distincted the things. It doesn't necessarily make sense when you do this to take to try and get everything in the data frame or in the SQL table, because really you're just looking for the output of 1 or 2 columns in terms of what you're looking for distinct, right? Okay. Assignment. This is basically the notion of creating a new column. So here I'm just creating a new column called name, and up here it creates a name, and basically I'm just comma spacing the usual way I might want to write a last name, first name. Again, nothing very complicated. Because I create a new column, it's fine. I can also use the assign statement, and that will also do the same kind of assignment. Here I'm making an uncivilized name which just has a colon in between, and I'm looking at it out over here, and here I can see the uncivilized name as the last column. Now, notice that over here I have an assignment on the left hand side, so it actually changed the data frame. Did I change the data frame on this one? No, right? So that's a gotcha you need to keep in mind. I'll confess that I actually got for a split second I got myself in a knot as well, because I said, what the hell happened out there? Why did this thing go away? But then okay, I have to assign it. Okay. One problem you have probably encountered in some of the Pandas stuff you've done in your homework already is that when you actually try and change an existing column, some parts of an existing column, it sometimes complains at you with a warning saying that you are trying to change a view on a data frame. Use lock instead. Use dataframe.lock instead. And that's what this thing does. So I just wanted to show this because you might have this gotcha in multiple homeworks. Lock is basically a location. The left side is basically trying to say what column you're on, and then what rows I'm looking for, and then the second part is what column I want. So here I want to look at all the rows which have the state of Virginia in them, and I want to look at the name column over there. And if I do that, I see this, and I want to, for example, I just want to name everybody who's in Virginia as junk, and then this is what I do. And this will actually change the data frame, not change a view on the data frame. So this is how you should assign to existing things. Okay, so now if I actually do a df.query with state of Virginia, you can see that the candidate that the name is junk at the end of it. Let's very quickly see this entire process in SQL, because it's this is the first time you're actually seeing how you might want to alter a table in SQL. So to alter the table, just say alter table, add column name. And by default, it's going to be a text column in SQLite, but you might want to say add column name int or varchar or something of that sort to specify a type for it. So here I've changed the table. I've added one more column. And I know I can add one more column because I'm doing this query of getting the pragma of the table info. This, by the way, is SQLite specific, and you'll have to, for every database, you'll have to figure out how to get the table information separately. Sometimes you can actually do just a select from the table, which is used to store the structure of the tables, to do this as well. And you can see that when I do this, it's going to add a column name over there. And it hasn't set any type or anything of that sort. So it's just going to take the default type, which in SQLite actually is a text type. So now I can make a query which takes the last name and the first name, and I can put them together by a comma and a space. And this way I can get a list of IDs over here for the whole table with the names and the IDs. And now what I do is, this is the second part in SQL. It's a little bit more complex in SQL. What I do is what's called an update. So you've seen inserts so far, when we try to populate the table, one line by one line by one line. But here I don't want to do that. I don't want to insert a line. I already have all this good information in the line. All I want to do is to update one column. So I have to use the update command. And the update command here says, it says update the table contributors. And when I'm doing that, set the name to be equal to something. But if I set the name to be equal to something, it'll set everything to be that name. And that's not what I want. I want the name to be set to something when the ID is that corresponding thing. And that's why I have those two question marks. And then I'm just going to take this tuple over here, and I'm going to put them in here. Because the first question mark is for the name, and the second question mark is for the ID. The first thing in the tuple is the name. The second thing in the tuple is the ID. And so that will update my, my table for me. Remember, this is a destructive thing. So what do I need to do? I need to commit, right? If I don't commit, this will not actually go through. OK, so I commit. And then I'm going to just do the select. And sure enough, I have this table. I have this additional column name inside the table. So we can do the same thing. We can actually set existing columns. So we might as well now do this for setting the name to be junk. And because the state is Virginia and the name is junk, I don't have to do any complicated stuff. Over here, it's a really simple update. So I can execute that, and I commit that. And then I ask for the select star where state is equal to Virginia, and boom, I have junk over there. So I've shown you now how to do this in two separate ways, one in Pandas and as well as in SQL. In Pandas, basically what you were doing is you were essentially using lock.lock to set the location if you were setting something that existed. And if you were creating a new column like name, you could just say df of name is equal to whatever you wanted to put it as. In SQL, you had to first alter the table to add one more column. You see, this is where it's a little bit more complicated than plain Pandas. And then you had to use update, and you had to use update and not insert because you only wanted to change one thing. OK. You can delete this column name in Pandas by doing something like this. In SQL, in most SQL databases, you are supposed to be able to do drop column name. So alter table contributors drop column name. But SQLite doesn't support it. So that's a kind of gotcha you need to remember if you're using SQLite. So I'm going to actually drop it in the Pandas data frame and let it be as it is in the table. I really don't care much about that column. It was just for demonstration. OK, I'm going to skip over aggregation functions because they're really kind of simple. In Pandas, you just do a describe. And in SQL, you just sort of kind of do max of something or min of something or average of something. And there are a whole bunch of aggregation things that you can do. But I would like to show you before we kind of wind up for the day a kind of a example of a what's called a sort of like a Russian doll subselection in Pandas as well as in SQL. So I could, for example, do the following command in Pandas. So what I'm doing over here is I want everything from this contributor's data frame, basically, such that it's less than the max of the amount minus 2300. It's greater than that. So I'm taking a range which goes from like, you know, the max contribution, which I think was like 4600 or something, minus 2300. So like from 2300 to 4600, and tell me all the people who've contributed that much money. That's what this particular command is doing here. And when I do it, I see there are two people, one with a contribution of 4600 and one with a contribution of 2600. If I wanted to do the same query in SQL, it's actually quite simple. I say select star from contributors where amount is greater than something, right? So one thing I could have done is I could have actually run that thing which is in the brackets out there first, got the results out, got them in Python, and put them right back in here using that percentage syntax that I showed you earlier. But you don't have to do that, and it's actually slower to do it that way, because what I'm doing in this particular example I'm showing you here is that I'm getting the database to do this mathematics for me, this greater than and something minus something else mathematics for me. So it's much faster at that end. And so what's happening out here is I say select in these brackets, select the maximum of the amount, and subtract 2300 from contributors. So what it's going to do is it's actually going to give me everything which is there, and then it's going to say select star from contributors where amount is greater than that. So it says, so again, select max of amount minus 2300 is going to actually select max of amount is going to get 4600. Then it's going to subtract the 2300 and get it to be 2300, and it's going to say select the one where the amount is 2,300 from contributors, and that's going to be 2,300. And then it's going to go select star from contributors where amount is greater than 2,300. So it's going to be exactly the same query that you did earlier, except that those first two queries are kind of numerical. And you can see that over here. For example, if I make this query and I say average of the amount from contributors, I get that. I get just one thing back. If I select max of amount, I get that max of 4,600 back. And then I do the 4,600 minus 2,300 and get the same result. So you can do things like min, sum, average. You should just do a Google search on SQL aggregate functions. There are multiple of them. Again, that depends on database. Some databases have many, many more functions defined as for the others. Finally, I can do a group by.sum in Pandas by using the group by thing. In fact, I can get a little bit more precise and say I just want the mean of, say, the amount, right? I can do a group by state, just get the amount column and get its mean. And then I can do the same thing in SQL as well by just saying select state and give me the sum of the amount from contributors, which is the whole table, group by state. It's just like dot group by state, group by state. So it's again a one-to-one correspondence between the Pandas data model and this. And there you go. The results are exactly the same. So let me stop out there. The big part that you should actually land up reading, there's more stuff out here in this notebook. But the fun stuff that I didn't actually have the time to get to, and maybe I can start off a little bit next time, or you can just read it, is things about joins between two different tables, which is when you actually want to combine information from two different tables together. Thanks, guys.